Welcome to N is for Networking, the podcast for folks new to the networking industry. And on this show, we talk about data networking fundamentals, explaining why things are the way they are and how they work. We deliver that information in plain English, keeping it as simple as possible without dumbing it down. Your hosts are, well, me, Ethan Banks, and Holly Metlitsky. I am a grizzled veteran of networking and recovering CCIE with decades of experience under my belt, and Holly is a fresh face hailing from Juniper Networks, where she works as a sales engineer and collects certifications like baseball cards. Actually, does anybody collect baseball cards anymore? Did I just reveal how old I am? I think I might have. Anyway, our guest today is Russ White. Russ is yet another grizzled veteran of the networking industry, having worked for several networking vendors, authored several books, and created many networking courses. He's also the host of his own technology-related podcast called The Hedge. And I'd say more stuff about Russ, but he's going to get even more embarrassed than he already is, so I'm going to stop now. Our topic today is responding to a listener's comments about models, which came in response to N is for Networking episode 5, which we titled The Sort of Useful OSI Model. And we're going to focus today on why we need models in networking. And we're going to read through some of the comments in a moment, but first let's meet Russ. Russ, welcome to N is for Networking, and you have strong opinions about networking models. So I thought a good way to have the audience meet you. Could you summarize how you think networkers should use models? What are they good for?
So for me, the biggest two things a model are good for, two big hits on models, are one, being able to ask intelligent questions. And if a model doesn't help you ask intelligent questions, then forget the model. It's useless. The second thing is to be able to understand the basic set of problems that need to be solved to get a thing done. Now, these two are interrelated. They're not completely separate. Like, you have to understand what needs to get done to be able to ask good questions. And so that's kind of where I come in with models, is that's their job.
I must say, I've never thought of a model as being useful to ask questions, and I really love that perspective.
Yeah. It's, for me, so I've been at this for a long time. As Ethan says, I'm grizzled. I have more hair than he does to be grizzled with, but we both have grizzled beards. You know how it is. Look at all the white in my beard there. You know, that's what happens as you get older. But anyway, as you go through life as a network engineer, you'll find that people invent new protocols all the time. It's like a little pastime of network people, of the IETF and stuff. Oh, look, I have the ABZ 5986 protocol. Look how beautiful. It's going to solve all the problems that's never been solved before by mankind. It's going to solve world hunger. It's going to be better than sliced bread, blah-de-da-de-da-de-da, whatever. And so what happens is as a technologist, as a network engineer, you run around going, oh no, I have to learn the new ABZ 5684 protocol. I have to learn this protocol and that protocol, and I have to learn how to configure it, and I have to learn, oh no, all this stuff. If you understand how to ask questions of the protocol, you actually don't have to care how to configure it, because the configurations fall out. You don't have to actually memorize the packet formats, because the packet formats fall out of what the job the protocol is trying to get done. And you can look at a sniffer trace, you can look at the packet format and go, oh, I see what they did there. Now, there's always going to be irrational stuff, right? There's always going to be fields that were stuffed in when somebody thought this was that and stuff like that. ISIS metrics, OSPF type 49 LSAs, or whatever they're up to now, 986, whatever they are. The EBIT, my wonderful favorite EBIT from the USPF world, but lay the irrational stuff aside, and you can learn 80% of a protocol by asking questions, if you know the right questions to ask. And you can do it in a week, 2 weeks, maybe even a day, depending on what the protocol is. You're not sitting there going, you don't learn by configuration. You don't learn by a packet format. You learn by figuring out what the protocol does.
I think that is a great tidbit of information for our listeners, and for me, actually, because it's not how I looked at things.
Always ask me if you want the sideways view, right, Ethan?
Yeah, that's fair. Sideways view, the jaundiced view, however you want to put it.
Yeah, exactly.
Okay, well, let's set up the rest of this discussion here by reading through some excerpts from an anonymous listener who sent us a lengthy set of comments about episode 5. That was our OSI model discussion. And so I'm not going to read the whole thing just due to its length, but there were some key bits here. So to quote our anonymous commenter, in response to episode 5 again, what I was hoping to hear is about the modularity of the OSI model and how one layer can be replaced and it won't affect items further up or down the stack. That's the real benefit to the OSI in my mind, is that I can replace a component or vendor or application and nothing else will care. Continuing, when someone is building a thing from the ground up, they absolutely need to keep in mind the OSI, because building a network from the ground up, build a storage unit, build the servers, the OS, the applications, any of those could more or less be replaced with something else. The ability to change either vendors or potentially other items is a huge benefit of the OSI in my view. No, it's not a perfect model, but it's kind of like algebra where we don't use it daily, but we think differently because we learned it. What's your take on those comments, Russ, and that modularity perspective especially?
Yeah, so modularity, we're talking about Liskop's substitution principle. If you want to go look that up someplace, that's kind of what we're talking about with modularity. And the end-to-end principle is in that realm as well, but it's another form of the same substitution principle and stuff. But so I would agree that it's very important to get into the modularity to understand. I don't know that the OSI model solves that problem very well, unfortunately. The OSI model, to me, if you just try to figure out how do you express what a tunnel is in OSI model, how do you express what MPLS does in an OSI model? How do you express what TCP does in the OSI model? And a lot of the problem is that IP came from the 4-layer model, what we call the DoD model, the TCP model, and OSI model came from OSI. Wow, imagine that. Which was ISIS, CLNS, CLNP, BGP, ISO, all those things in that side of the world. And it actually came out of a database view. So if you think about, there are 3 different ways to transfer data between 2 computers or 2 systems, 2 applications, whatever you want to say. The one is you can put information in a socket and it comes out another socket. Okay. Another one is you can put information into a function call. Now, socket to socket is what we typically call like just transferring like FTP data, something like that. You can put it into a function call. You call a function on the other machine. It comes back with a response. That's a remote procedure call. Then finally, you have what we see with RDMA and more modern stuff, which is I put it in a virtual memory page and I actually access the virtual memory from some other computer. That's the 3 basic ways you can transfer data. OSI is built around a socket model, not an RPC model, not a DMA, not a memory model. It was built by folks who were building database systems. So it tends to get wrapped around that database system view, and it tends to be less than useful in other areas. That's my whole thoughts on the OSI model. Now, I'll be honest. I learned the OSI model going through my CCA. And I'm so old, we didn't have CCNA and CCNA and CCNP. There actually wasn't even a JCNIE. There was nothing. There was CCIE, and that was it. But I learned it going when I was in Cisco TAC and all sorts of places. It took me a long time of looking at the OSI model and realizing I actually don't use this for troubleshooting. I actually don't use this when I design networks. I'm in the IETF. We actually don't use it for protocols. So what am I using this for? What is this here for? Which made me go seek out other options in terms of models.
I think I've had the same experience because my learning started, the first thing I learned was the OSI model. And as you start getting into the nitty gritty, I've had the same thoughts where I'm thinking, okay, I've got this idea in my head of this model, but I use it to revert to layer 2 or layer 3. That's really that's where I use it.
Yeah, exactly.
So what else, I guess, in that line, where do you think that benefit then comes in, apart from just your understanding in a practical sense?
Yeah. So the OSI model, the thing I think has always been great about the OSI model is it introduces the network engineer to the idea of layers and layered functionality, that you have a physical layer with a physical and a data link component of that physical layer, et cetera, et cetera. I think that has been a very good side effect of the OSI model, just to get people to think about substitution, think about modularity and in a vertical way. But I think that it becomes so confusing in modern networking that it becomes very difficult to apply beyond just saying there are layers. Yeah, there are layers. I don't know what else I get out of it beyond that.
Think specifically about VXLAN EVPN. What happens to the OSI model in that context?
Yeah, that's what I was saying, like MPLS.
Mm-hmm.
What do you do with MPLS? Oh, it's a layer 2.5. Well, kind of depends on how it's being used, doesn't it? It could be a layer 3.5. It could be a layer 2.5. And if I'm doing 0.5 layers, like there's something broken. Like I shouldn't be doing 0.5 layers. And VXLAN, anything tunneling, describe tunneling. Well, tunneling is what? When you put IP over, or when you put Ethernet over IP. So when you put layer 2 over layer 3, except there are cases where it's layer 3 over layer 3. Well, you know what I'm saying? Like this gets hard. It's very hard to describe certain things in precise technical ways, which, by the way, most people in networking don't care about precision technical ways of doing it, right? We don't care about precision of language, which is like a total pet peeve of mine. What's a layer 3 switch? I'd stop it. Just stop it. Okay. I aggregate and I summarize in OSPF, but they're interchangeable. No, stop it.
Now, you said something earlier about how you use and don't use the OSI model. And I believe you said, I don't use the OSI model when I design networks. I don't use the OSI model particularly when troubleshooting.
No.
Okay, so we could use models for those things. Where else
Yes.
might we need models as network engineer? What other knowledge domains?
Well, I do use a model. It's not the OSI model.
Right.
So I'll say that. Other places, I think it's really important to have models of, in the networking domain, are things like models of how a router works. I put packets in here, they go out there. I need a model of what that internal thing looks like. Now, it may not always be true. It may not match every piece of hardware that's ever been produced, but that's not what a model is, right? A model is an abstraction of how 80% of the things are going to work. And so if I'm going to design networks, I'm going to troubleshoot in particular, I need a mental model of like routing table to fib to forwarding engine to input queue to output queue to PHY chip. Like I need a mental model of what that thing looks like. Again, it may not always be the same. There may be things in different ones, but that's okay. I need a model of how I build an encrypted session, right? What is the general process, regardless of how you do the keys or whatever? How do I find a public key for the person I'm going to talk to? How do I exchange private keys in a secure way? How I rotate private keys? There are specific protocol changes, but I need to have a model of how that process works. For routing protocols, I need to have a model of like, how do I exchange routes? How do I guarantee that everything is consistent in the network? And what does eventual consistency look like? So I need models. I need lots of models for all sorts of things. But you have to find models that are useful to you, that help you ask the right questions and to troubleshoot. And not everybody's going to have the same models that they're going to work for them.
Just thinking of all of the specifics that you've mentioned there, what immediately comes to my mind is often when we think of models, we think of something like the OSI model, or we think of actual formal models. But a lot of the processes that you've mentioned come back to just you creating your own personal model based on your understanding. And that's really beneficial.
Yeah. Oh, you can learn a ton by building your own state machine, right? Take BGP, write your own state machine. Totally ignore every textbook in the world. Write your own state machine of how BGP builds a peering session, runs best path, right? You'll learn so much by doing that. I would actually, and people are going to really push back on me about this, I would actually say you'll learn more doing that than putting Wireshark on the wire and watching the packets flow by and decoding the packets and understanding the way the packets work. Now you can build the state machine. In fact, a funny story, when I first started working for Cisco, there was no documentation for EIGRP. Literally nothing. No white papers, no internal. There was Dijkstra's original paper. There was the source code. That was all there was. So Don and I, what's his last name? Anyway,
Don Sharp?
No, not Don Sharp. It's a different Don. Don Slice.
Oh yes, okay.
Don Slice. Yeah. We used to call his kids the slivers. But anyway, so Don Slice and I took and wrote and compiled a special image of iOS with breakpoints in EIGRP, and then we put a sniffer on the wire. And by the way, the sniffer decoded the packets wrong. The sniffer didn't know EIGRP well enough to decode the packets correctly. But when we hit a breakpoint, we would watch the packet that was ejected, go back and look at the code on how that packet was put together, and then we could watch EIGRP do flooding. And we built a state machine of how it worked because the code itself in EIGRP was quite complex. There were places in the code where I would actually ask somebody who had written the code how this works. And their actual response back to me was, "Oh, you hit that, did you? Yeah, good luck." So yeah. So you can build models that way, right? It's hard, but you can build models that way. But you're right. You're right, Holly. Build models. You'll learn. It's really important to go out and build these for yourself. Have your own personal sets. Okay, if you don't agree with mine, that's cool. That's good by me.
Now, Russ, you and I taught a course together. So it was several years ago. I think it ended up on O'Reilly, but we were talking about transports, IP-based transports, and we got into the RINA model at that time, RINA. And I think you've evolved you liked the RINA model at the time, but I think you've evolved your perspective. Could you talk a bit about the RINA model and then what you've evolved to?
So the RINA model is, and Holly, you need to feel free to step in here, because Ethan and I will just like jabber and
I told her this before the show, so yes,
we'll
please
just
do follow.
jabber and
butt in with questions.
Be what it is. You gotta just like jump in and don't worry about interrupting anybody here, Holly. So anyway, the RINA model was designed by John Day. And for those who don't know who John Day is, he wrote Patterns in Internet Architecture. And this model is as old as the OSI model is. We just don't know it. It's an old model. It came out of, there was a time when there was a TCP/IP model, DoD model, OSI model. There was a competition over, not really a competition, but like a popularity contest, right? Like you vote for the homecoming queen and king or whatever it is. And the OSI model won that competition or that popularity contest or whatever it is. But John Day had proposed the RINA model. And the RINA model essentially says there are 4 problems to solve. I need to solve multiplexing. I need to solve marshaling. I need to solve error control. I need to solve flow control. Those are the 4 things I need to do. Now, observationally, I note that 2 of those, multiplexing and marshaling, tend to be implemented in a single protocol. And observationally, I note that flow control and error control tend to be implemented in a single protocol.
Okay, now those are technical terms: marshaling, multiplexing, et cetera.
So let me
we got to walk through those.
I was about to say, I don't think I've actually ever come across marshaling.
Yeah, okay. So marshaling just means, so he doesn't call it marshaling. If you go back and read his documentation, he calls it transmission. I don't really like the word transmission because it's not very descriptive. I tend to use the word marshaling. Marshaling is basically your grammar and your dictionary. When you write a sentence on a page, you are marshaling the data in a way that a receiver can pick it up and read it.
This is a noun, this is a verb, these are adjectives. Yeah. There's a grammar to it, a structure that is predictable. And so you're looking at that, and you used English as an example here, and know how to parse what you're seeing.
That's right. Yeah. So I call that marshaling. Again, he calls that transport. It's just, I don't like, the word transport is way overused in networking. So I don't, it's not a word that I like to use. But anyway, so marshaling just means this is how I put the data together as a transmitter so the receiver can understand it. Multiplexing basically just means I need a way to pick out the set of receivers that need to hear the data I'm about to send. That's all it means. So it's addressing, it's routing, it's all those things. The example I like to use is you walk in a room and you say, "Hey, Joe." And the right Joe answers. Well, how does that happen? Because they recognize your voice. You're in a shared medium. You're in the air. There's 1,000 people talking in the room, but they recognize your voice and their name, and bada bing, they know who you're talking to, right? That's multiplexing.
So this could govern broadcast versus multicast versus unicast. It brings in addressing and the addressing schemes on some level. Yeah.
Exactly. All of those things are under multiplexing. So in my mind, multiplexing is the hardest problem to solve because it does cover so much stuff. And then error control and flow control are very simple, right? It's flow control is that crazy ant that you talk to who tells you the story the 15th time, 10 times faster than you can understand it. And you're like, stop, right? That's flow control. and error control is just what it sounds like. There's got to be some way to say, no, I didn't receive you correctly. Huh? What? Can you repeat that? Right?
Both of which, if you're new to networking, TCP involves, if you study how TCP works, there's lots of flow control and lots of error control happening, Holly, like with ACKs and selective ACKs and so on.
Yeah. So those are the 4 basic things he said needs to be done. Now, his observation is that you do these 4 things, interface to interface, PHY chip to PHY chip, physical interface to physical interface, host to host, and application to application. Now you have 6 layers. Because
that is, those 4 things happen at those 3 distinct endpoints of communication: app to app, host to host. What was the other one again?
Interface to interface. Interface to interface.
Right. Yes.
Yeah.
Yes. Right. Those 4 things happen, and you pair them, right? So you have 2 protocols at the physical layer, 2 protocols at the host-to-host layer, 2 protocols at the app-to-app layer. So you have 6 layers, 6 protocols in effect. It's not perfect. There are places where you have 7. There are places where you have 8. There are places where you have 4. But it's cool. Those are the basic problems you're solving in all 3 of those realms.
So let's walk through an example that would be very common. Talk us through an HTTP transaction.
An HTTP transaction, you build an Ethernet packet, which has all 4 of those problems solved using data link and physical signaling, that you send to your router upstream, right? And then your router uses that some physical pair of protocols to reach, hop through the network. Then you use IP and to some degree TCP. This is where things get a little bit sloppy, but IP, which tells you which physical host you're trying to get to or which virtual host you're trying to get to, which service. And then there's a protocol number in IP that is a multiplexer for the processes sitting on that host. And then the TCP runs application to application. From the host level, it has no clue what's going on with TCP or HTTP, right? It is nothing. All it knows is IP. And it goes, oh, I have IP with this protocol number. I'm putting that in the TCP, little TCP thing. And the TCP queue says, oh, that's an HTTP thing. I'm going to stick that in the HTTP queue, right? So this is all totally transparent. Like it's a total opaque box from above. And from the bottom, it's a total opaque box as well. The Ethernet process doesn't know what it's carrying. It doesn't have any idea what it's doing, right? It's carrying ones and zeros. They're randomly formatted as far as it's concerned. So this is how RINA or RINA, however you say it, recursive internet. I think he says RINA, but anyway. Now, John Day will argue there should be 8 layers, but let's not I'm actually rather ambivalent about the number of layers. I could care less.
So let's pause here, Holly. I've seen you nodding, but your brow is also furrowed at the same time. So let's deconstruct this. What questions have you got?
I don't even know if I have questions at this point. It's quite funny because my brain is like, okay, constantly trying to compare this back to the OSI model because that's what I know. But it's, to some extent, I think I understand it. But the protocol part, I think, is where it gets a little bit fuzzy for me, where you were saying that you have like 2 protocols at each process.
Yeah. Right. So Ethernet has a physical protocol that you've used to physically put optical or electrical signals on the wire, right?
Yes.
Then Ethernet has a second protocol that we don't ever talk about. It's hidden. It's called data link. Now, when I was getting into networking, we talked about data link a lot. Nowadays, we just treat Ethernet as a thing. But technically, data link layer handles whatever flow control you might have on Ethernet. It also handles whatever error control you might have. However minimal that is, that's what it does. Now, if you go to the host to host, you can say IP and TCP, right? I can say, right, I have multiplexing through IP and TCP handles my flow and error control. Now, when I get above that, I go to HTTP. The confusing thing is HTTP has all 4 of those rolled into one. It's one protocol instead of 2, right? This is where you need to always think this is a model. It is not a perfect description of the world. It is here to allow me to ask questions.
There won't always be some unique function mapping to error control, flow control, etc.
Right. Yeah.
Yeah.
Or
I guess
protocol.
Following on that, why do you prefer this to the OSI? What specific features of it do you find more useful or beneficial in whatever you use it for?
Well, because again, when I go back and I'm troubleshooting something, I'm trying to understand a protocol, right? Say I'm trying to understand a new transport protocol. Well, I know the 4 problems it needs to solve, right? How does it marshal? How does it multiplex?
Yeah.
If I know those 4 things, I know the protocol. Whatever the packet format looks like, however you configure, I really don't care. What I care about is how it solves those 4 problems. And I can do that with, like, you can hand me, oh, I have this new optical network thing. Great. All right. It's host to host, or it's interface to interface. It's a physical layer protocol. I need to know how it solves these 4 problems. And the answer might be, it doesn't solve problem number 4. It leaves it for an upper layer. Okay. That's a valid answer, but it's an answer that helps me understand the protocol. Right. And that's where I find it really useful. And troubleshooting.
It's a different way to think about networking in that it's recognizing a common set of problems that networking needs to solve.
Yeah.
And those those problems are common at different layers.
Yeah.
We always have to deal with marshalling. We always have to deal with multiplexing and flow control and error control. And those things happen again at different places in the stack. If you assume that these are the 4 problems that need to be solved, you end up with a model, a framework to analyze the protocol and figure out, all right, what are the features it has that is addressing those issues? It's a different way to ask questions and get answers than the default. Where does this map into the OSI model? It's just a different way to think about that. Yeah. And the answers to those questions can help you map that protocol onto the OSI model too, by the way.
Yeah. Oh, yeah. Yeah. I don't know that mapping on the OSI model actually helps me understand the protocol better. That's where I get like lost on the OSI model. Right. To be able to say it's a layer 3 protocol, what does that actually tell me? Like that doesn't really tell me anything. Whereas if I say,
I'll disagree with you, Russ, because what it tells you, if you're coming at it from, I'm a network engineer trying to figure out the big wide world, it's helpful to know, oh, BGP is something I might use alongside of or instead of OSPF or ISIS or another routing protocol. It kind of, if you understand OSPF and you want to compare this new thing to something you're already familiar with, it could help you in that regard.
Now, the way it would help me, the OSI model would help me is I would be able to say layer 3 protocols only touch host and routers. Layer 4 protocols should, in theory, layer 5 and 6 or whatever, should, in theory, only touch host with applications, right? So I know if I have layer 3 connectivity, but I don't have layer 5 or 6 connectivity, now I know the problem is not necessarily in the network, it's in the host. It's not necessarily true, but it can be helpful. But that's really the only place I've ever used it. So that's why, like, with the RINA model, I can actually say this is a layer 3 protocol. Well, layer 3 to me means IP again, because I have 2 Ethernet protocols, my first 2 layers. Then I have IP, TCP, or UDP, or QUIC as my second 2 layers. Layer 3 is still IP. I can say, all right, layer 3 solves 2 problems out of the 4, which are multiplexing and marshalling. Basically, now I'm going to have marshalling and multiplexing above that as well, but they really bleed into the upper layer. Again, you have to be flexible with the way that you're asking the questions. It's a model. It's an abstraction. All non-trivial abstractions leak. I don't know how to solve that.
I think if I had to wrap this into like my own understanding of the RINA model versus the OSI model, correct me if I'm wrong, but to me, it seems that the RINA model is more functionally based. What exactly are you doing? Where the OSI model is really, it doesn't answer that question. It tells you, sure, the layers and what goes on, but it doesn't tell you why. Like, why do you have IP or why do you have this at layer 2? Where I think the RINA, where you look at multiplexing and marshalling and the other 2, it's actually saying, okay, well, this is the purpose. This is the purpose of IP, where OSI is just saying, okay, well, you've got 7 layers. Have fun.
So the way I would describe it is OSI model describes the interfaces between the layers.
Yeah.
The APIs.
Yeah.
The RINA model describes what the layers are doing and doesn't care about the interfaces.
Mm-hmm.
Right? The RINA model does not tell you anything about the APIs. The OSI model is really based around, from a programmer's point of view, what is a socket? Right? What is a queue? That's where it comes from. And so I'm not saying it's totally, it has its uses. Just for me as a network engineer, I tend to find the RINA model a lot more useful in my experience. And
are there any other models?
Well, so I'll tell you, I've extended the RINA model. I now call it the 4 things model.
Okay.
And the reason I do this is because I observed, I started building my own little chart of like, okay, how many ways can you multiplex? Well, you have what problems do you need to solve when you multiplex? You need to name things, you need to map things, and you need to route things, right? Those are the 3 problems I need to solve. When I look at naming, there are only 3 ways to solve naming. I can calculate the name, I can distribute the name through a protocol or through a service, or I can discover the name through a protocol. That's the only 3 solutions that I know of. So I can actually build a mental map of the entire problem and solution space of every network protocol that's ever existed. And I can say, okay, you're handing me a new routing protocol. Great. There are 4 problems the routing protocol needs to solve. It needs to discover the topology, it needs to advertise the topology and reachability and topology for both of these. It needs to calculate a loop-free path, and it has to have policy. Those are the 4 problems a routing protocol solves. If you hand me a brand new routing protocol, I can ask those 4 questions, and I can tell you how the protocol works. And by the way, for each of those, there's only 2 or 3 solutions for each one of those problems.
In general,
in general, there are odd cases, but in general, how do you find a loop-free path? You record the path, you run Bellman-Ford, or you run Dijkstra. Those are your 3 options. There are some other odd ones.
For example, people that have studied OSPF and ISIS, very extremely similar, not identical, but very similar in how they solve that problem, for example.
Yeah. It's more of a marshalling difference between those two protocols than it is a shortest path first difference by and large. So this is where I think the model really helps me, is that people throw new routing protocols at me. I read research papers and they're like, we invented a new routing protocol. Good for you. All right. How does it do those 4 things? And that's all I care about.
And there's a bigger point here in that it can be intimidating as someone new to technology in general and networking specifically. You see all these different protocols and all these acronyms. But Russ, the point you're making is you can boil down a lot of these and once with this analysis framework, with this model in mind, and figure out, oh, this is like that other thing. They're really similar with a couple of interesting differences, perhaps. It's not so this massive amount of acronym soup that you see that's so intimidating, it actually isn't that intimidating, because once you get into it, you realize how similar acronym soups are one to another. And once you have that framework, that model to know how to think about something, you're going to see patterns, repeated patterns over and over and over again. And the learning them is like, oh, once you've learned OSPF, you kind of know ISIS. Yes, there are crucial differences you need to understand, but 70% of what ISIS does is going to look just like OSPF. And then from there, it's just figuring out, as you said, like some of the marshalling differences and so on.
Yeah. And even if you know SPF really well, you know why ISIS does partials and OSPF doesn't. Like it just falls out. It's like, oh, yeah, now I see why that could be. Now I'll give you a perfect example of what you're talking about, Ethan. Way, way back in the frame relay days. We had a problem with broadcasting unknowns on point to multi-point frame relay. So we solved that problem in a particular way. Now, when ATM came along, yet another dead technology, we had a problem with broadcasting unknowns and multicast, bum channel, as we call it, broadcast unknowns and multicast. And we solved it exactly the same way we did in frame relay. And then when Dino Ferranici designed Lisp, he had a problem with broadcast unknowns and multicast, and he solved it exactly the same way that frame relay did. And then go look at EVPNs. And EVPNs have a problem with broadcast unknowns and multicast. And guess what? It's the same solution. They've used the same solution going back from the 1980s to modern protocol. It's exactly the same solution. It uses different frame types. It uses different numbers. It uses different packet formats, blah-de-da. I don't care. It's the same solution.
Yep.
I think this conversation has really changed my perspective on a lot of things, I must say.
Oh, no.
I'm very, no, really in a good way, because when I first came into it, it was very much how you started this conversation of what you shouldn't do, which was, here are a bunch of protocols and here is how you should configure them. And I thought, oh my gosh, I've got to learn the configurations for every single one of these. And I never really thought about it like, okay, well, they all kind of do a similar thing, and look at it from that. And whatever configuration, sure, you can learn how to speak another language, but you can communicate. That's the base of it.
So shameless plug. So Holly and Russ and I are on a Zoom session here, dear listener, and over Russ's shoulder is Computer Networking Problems and Solutions. That's the book Russ and I co-authored. I don't know, it's been 5, 6, 8 years, whatever it's been. But the premise of that book was not to show you how to configure everything. There's probably some configurations in there. I don't even remember at this point. But it was to teach you how to think about a certain problem, and then with the understanding of the problem space that was being addressed by a particular technology, have a framework to know how to use it and what it does, not what commands to type. The commands you end up typing, yeah, they're important, but they're incidental, honestly. Understanding the problem and the different ways you could solve that problem are the key. From there, you understand the configurations that you're looking for so that you can execute the solution to the problem you've selected.
Yeah, I'll tell you another place this is really, really cool is when you design networks. You actually now know the limits of what the protocol can do. And this, I mean by this, right? when you think, go back to ATM or go back to frame relay, ATM, Lisp, EVPN. Well, I was around during frame relay. I know, gray beard, nonsense stuff, whatever, right? When you see that broadcast and unknown solution fail, you now know how EVPN broadcast and unknown is going to fail. It's going to fail exactly the same way. Again, if you understand shortest path first, then you can take any protocol that's SPF, OSPF, or ISIS, and you can say, now, what are going to be the logical limits to designing a network? Like people say, oh, I can only design a floating domain with 50 routers in it. Why? Like what intrinsically in the protocol stops you from doing that? Nothing. Okay, there might be processor issues. There might be, but let's get past the hardware for a moment and realize the protocol is not limited that way, right? And you can suddenly say, well, how big of a floating domain should I make it? Well, how does Dijkstra run? When would Dijkstra hit the wall? How would you know Dijkstra's hitting the wall? Oh, you'd see your SPF runtimes go up. Well, now I know when I'm designing the network what to look for a particular failure mode and how to design my limits. So this is really impactful in the design and architecture realm. It's very impactful in those realms.
Russ, you talked about RINA. You talked about your advancement on that of the 4 things model, which allows you to kind of map, 4 crucial things and then think about it from that perspective. For homework for our listeners, are there any other models that they could look up or worth considering to educate themselves better beyond the OSI model?
Well, again, going back to the beginning, I think it's really important to build your own, like start from the RINA model and build your own 4 things. Like figure out what they are. Think about, even in the OSI model, how would I describe a tunnel in OSI? What would I do? Is there an effective and rational way to do it? I'm not saying there's not. I'm saying you need, like, these are mental exercises that help you understand. Build a model of your own state machine for BGP, your own state machine for Dijkstra, your own state machine for starting an encrypted session, like for DNS. Build your own state machines and understand them. Don't just rely on, I publish them a lot, on blogs or whatever. I'll just give you the RINA model and my 4 things model. I don't think that's nearly as effective as you sitting down yourself and saying, all right, this is how I think a router works. Right.
And the natural question a listener is going to have is, but what if I'm wrong? What is your response to that?
Go ahead, Holly. I think you already know the answer to this.
I was going to say, good.
Yeah.
It's how if you write all the time, you learn nothing.
Yeah.
From firsthand experience.
Yeah.
You never learn anything when you write.
Yeah. It's a model, right? Apply it to the real world and tune it as you figure out how you've made mistakes. That's what you do.
Yeah, I've learned the most valuable things I've learned over the years when things break, when I got it wrong, when I didn't consider a certain situation, and then all of a sudden I was faced with it, etc. Yeah, if you haven't failed in networking, you haven't been around long enough, or you got to try harder.
Yeah, I was going to say, I haven't been around that long, and I already have, so I'm on the right path.
Yeah, oh yeah, definitely. And don't be ashamed of the failures, right? It's a learning. It's what it is, right? People get off, oh, I failed. Oh, I'm a terrible person. No, you're not. I failed my CCIE exam the first time I took it. Okay, get over it. Whatever. I think Alan took great joy in failing me on my first CCIE attempt.
If you're Russ keeps throwing out first names of all these people he knows, he does that, but
sorry,
Alan, as in the CCIE proctor you would have been working with back in, this would have been early CCIE, probably V1, V2.
This was the only CCIE proctor in 1996 when I took the CCIE.
So V1, yeah.
Yeah,
okay.
So V1, yes. Yeah, when we had the 60-pin cables and they would push the cable pins in so it wouldn't make a connection.
Yeah, because they'd break the lab during lunchtime or something like that, or overnight before your second day.
Even worse, they would actually have all these Ethernet and 60-pin cables hanging up on a rack and half of them wouldn't work. So even when you were building, you were building with often broken equipment. Certain ports just wouldn't work in the hardware at all. And then, so it was like you were troubleshooting the whole time you were building. And then they walked in and they broke it. Yeah. And so I had named all my 2501s 2501A, 2501B, and he changed the host names to 250 lowercase L, A, and B to break my lab. Yeah, that was entertaining.
Oh, wow. That's mean.
Yeah, I had a V3 CCIE lab, and they didn't break things for you. There was plenty enough of troubleshooting that needed to be done in that lab, but they did not actively break what was already there. Because I think at that point it might have been virtual lab equipment. I'm not even sure.
Yeah, it might have been.
It goes back to 2008. I don't remember anymore.
No, when I took it, there was one 7 router rack sitting in a room in Raleigh, and one proctor. And that was the whole thing.
Yeah. Well, Russ White, where can people find you on the internet?
We can just look me up. I'm pretty easy to find. Find me at rule11.tech. I try to post everything I post everywhere onto Rule 11. I don't do as much blogging as I used to. I need to get back to it. I'm just writing other stuff so often now. I write for Packet Pushers every now and again.
You do. And in fact, some of your most recent posts were about how to think about network models. So you can go to packetpushers.net, search for Russ White. You'll get his author page and can search for, and then you'll see the writings that he's done recently on network models. And we'll also remember to include those in the show notes for this episode. Yeah.
And you can find me on Twitter, X, as Routing Geek. So.
You're actually active on X? You using it?
I occasionally log in under Routing Geek. I have another account that I use more regularly, but it's more for theology. So,
okay. Well, Russ, thank you for joining us today. It's been a pleasure as always. Holly, any parting thoughts for Russ or questions you might want to ask?
No, I think I need to get my hands on your book, both of your book. That's where,
One of the nice things
takeaway.
about not having too much configuration in there is it's got longer shelf life for sure. If you're like, it's an old book, they published it, and I think it was 2018. Now that I'm thinking about it,
2018, yeah.
Yeah, but it's still a lot of it's quite relevant. No, we're not talking about EVPN VXLAN in there, at least not in any detail, because that was an emerging technology at that point. But we hit a lot of stuff that's still very applicable for the day because it teaches you how to think. So
and I think that's what my biggest takeaway from this conversation today is really starting to change the way I think about things.
And Holly, I'll just say if you have any questions, you can rely on Ethan, of course, because he's got the gray beard, but feel free to reach out to me. I'll say the same thing to listeners. I mean, you can find me on LinkedIn. I do try to answer all the PMs that I get on LinkedIn or DMs or whatever they're called, and emails and stuff. So feel free to hit me with questions if you have questions about this stuff, because I'm always happy to be as helpful as I can.
Well, again, Russ, thank you for joining us. And to you out there listening, thank you for listening to NS for Networking. Holly and I are going to chat with you again next week. We're going to explain more jargon, concepts, and big ideas from the world of packets. If you have questions, comments, or a topic request, let us know at packetpushers.net/follow-up, and we will do our very best for you. If you'd like to connect with me or Holly, you can do so via LinkedIn or the Packet Pushers Community Slack group, which you can join for free at packetpushers.net/community. And by the way, packetpushers.net, we got a ton of 100% free resources for you as you grow yourself as a networker. There's no login required. There's over a dozen, there's exactly a dozen, not over a dozen, but exactly a dozen podcasts that go as deep as you might want to get, including a huge backlog of literally thousands of episodes for you to search through. We've got weekly newsletters that help you keep up with what's going on at Packet Pushers and in networking. Our YouTube channel has demo videos and mini courses, plus our entire podcast lineup published as audiograms. Please share NS for Networking with your colleagues. We would really appreciate that. And just remember, networking isn't hard. Other people figured it out, so you can too.